Okay, you guys missed the interesting video, but we're going to move on. Right, so hydraulic press, right, is hammerhead is 200 kg lifted 3 meters from the top of a vertical I-beam and dropped into the ground. The hammer has been dropped, driving I-beam 7.4 cm further into the ground. The vertical rail guides the hammerhead, has a constant friction of 16 newtons. Use the work engineer to find the speed of the hammerhead just as it hits the I-beam. Right, so it loses 3 meters worth of GPE, right, gravitational potential energy, convert that to Ke. Not a big problem. You have done this in secondary school, so I'm not going to bore you. Answers are easy, right? Except that you also have friction, right? So you must remove the energy. So part of the GPE goes towards overcoming friction, the rest goes towards Ke. Right, so there you have it. mg h minus force times distance, friction times distance equals to half mv squared. You can find the v to be 7.55. Not a big problem. Questions? Okay. Part B. Part B asks you to find the average force as the hammerhead exerts on the I-beam. Ooh, that's fun, right? So it pushes down the I-beam a further 7.4 cm, which is not a lot, right? 7.4 cm is something like that. But considering the amount of forces involved, it's actually quite an interesting idea. Right, so what is the force exerted during the motion? So of course, we must find the average force, right? As I've said just now, the force should be a curve, but let's find the average force. So here, right, the net downward force will be mg minus f minus n. Well, energy theorem, right, is kinetic energy at point number 3 minus kinetic energy at 2. This gives us this equation. Right. Working this out, N is the force, right? N is actually the force of the I-beam on the pile, on the hammerhead. But using Newton's third law, we can say that it's also the force of the hammerhead on the pile. Right? So we find N is actually 7.9 times 10 power 4. Right? There are more intuitive ways to explain this. So they have possessed a certain kinetic energy, right? The kinetic energy and the extra 7.4 cm worth of GPE that we will lose are the things giving away energy. What takes the energy? Right? It will be the friction, and second, it will be the force times the distance by the pile, right? The force N of the pile on the thing times the distance of 7.4. Right? So that's the other way to look at it. So you think of it as who's giving the energy and who's taking the energy, and you separate out that. Right? So you could use the work energy theorem if you are comfortable with that, or you could use a more intuitive method if you think of physics like that. Either way, you should arrive at this answer. Questions? Okay, good. Okay, PE, simple stuff, moving on. GPE, simple stuff, moving on. Okay. Okay. This simply means that there's a conservation in the mechanical energy, where the loss in one will become the increase in the other. Right? Simple like that. Okay. Okay, let me go a little bit slower. No other forces. The total work done equals the work done by gravity. Change in GPE. Are you all frustrated? Too fast? Too slow? So total work done is a change in K, but the work done is actually provided by the GPE. If you rearrange, it becomes like that, which is what you have learned in secondary school, just that we formalize it under the work energy theorem. All right, and you realize that your conversion of energy actually comes from the work energy theorem. If the force is not equal to 0, then of course then there's some other forces included. The work total is the other forces plus the work done by gravity, right, which allows you to have all this. Okay. If your other forces by your work is positive, your final energy in terms of kinetic energy and work potential energy must be bigger than initial. Right? That's essentially what these symbols are saying. If the work done is negative, that means you're taking energy away from the system. Your final kinetic energies and potential energy must be smaller than what you have at first. So I'm just converting the symbols to language. Boring. Mechanical energy is defined as the sum of kinetic and potential energy. Okay. Alright, conservation energy. Oh, okay. Fun stuff. This was a bit more fun. Right? This equation that jumps out at you, you'll be like, what is this? This is gravitational potential energy in the scale of planets. Right? When we learned GPE is mgh, the G does not change because G on the surface of Earth is relatively constant. G being gravitational field strength. Right? Gravitational field strength in the scale of planets actually becomes smaller and smaller. The pull on the object becomes smaller as you go away. This is a new equation that you need to learn, right? Later on, I will elaborate a little bit more on that. That gravitational potential energy is described as GMM over R. Okay? But the same thing is true, right? Same thing is true using work energy theorem, right? The total initial energy is equal to the total final energy, right? If there's no other forces acting on the object and the planet. Right? So this is considering the kinetic energy of the object in relation to the planet. Okay. Am I speaking Greek to you? No, because these alphabets are still not Greek. Okay. Obviously, too early in the year for this kind of jokes. Right, average power. Average power is defined as the change in energy over the change in time, right? Or rather the change in work over the change in time. Not a big problem. One is equal to the other. One of the common things that actually stumps our Olympiad students, surprisingly, is this unit, 1 kWh. 1 kWh, is it the energy of, is it a unit of energy, power, or time, or what? Really? Yes, it's true. Because I've already done the conversion here. Okay. So actually, your household bills, if you go and ask your friends, if you don't have a household bill, go ask your friends who actually parents receive a household bill. It's actually built in kWh. Okay, kWh. So my personal shock is that I've learned something. I bought my own home recently, right? And I got my first 3 months of electricity bill. So I had almost no electricity usage in the first month. I don't know why. In the second month, I had a very, very, very large electricity use, like way beyond the national average. Then in the third month, I have almost none again. So I was looking at this and like, why is that? Because I stay there, right? Unless there's someone else inside my home, right? Cannot be. I mean, that's my wife, but my wife and me, we use the electricity the same way over the 3 months. So the realization is that the utilities, right, PUB, they actually only look at your meters every 2 months. So they take averages. So they somehow averaged it out and then guessed. Because in the first month where it's empty, I was actually using it. So they didn't read the meter. So they compiled that and put it all into the second month. So it's a very strange thing that they're doing. Anyway. Alright, on more serious stuff. The human heart is a powerful, extremely reliable pump. Each day it takes in and discharges, blah, blah, blah. How much work does the heart do in a day? Not not the herd. What is its output power? Okay. You all have this, right? In your, I mean, you already have answers, so I'm not going to bore you all, right? So let's first calculate how much liters or what's the mass of blood it leaves in a day. Are you surprised at the amount of mass that your heart leaves in a day? Does this make sense? Does this make sense? It makes sense, right? I mean, you are taking mass, right? You convert the liters to meter cube. Like liters is a measurement of volume, right? Very useful for your water bottle, 1 liter. But you need to learn how to change it to meter cube. Meter cube times density gives you the mass, right? So it's not that bad. This makes a certain interesting assumption. The average American female, the heart is here, right, on the head, right? Which is a pretty strange assumption, but assuming that it's true, the work done is 1.26 times 10 to the power 5, which is quite a lot. Okay. Right, how many of you have your heart right here? No, right? What is the power output in watts? Just divide that, the total energy divided by time in seconds, you have it. Right, so although it looks like it's producing a lot of energy, it's over 1 day, the power of your heart is actually not that much. Okay. How many of you have actually gone into a room where there's a lot of people and you felt like it's very hot? For example, the hall, right? All of us, right? The human, right, is actually like a 100-watt light bulb. So you're producing heat like a 100-watt light bulb. So 2,000 of you in the hall is 2,000 times 100. That's how hot your guys are.
But that is not true in LT5.
Yes, that is not true because the aircon, well, you are still producing that amount of heat, maybe even more to keep. Yeah, but LT5 just sucks it all away.
Sure.
Yes, we're actually harnessing your heat energy for no lah. We are not Harry Potter or that stuff. Okay, yay. Circular motion. I think this you have not learned in your secondary school, so we should spend a bit more time here. Oh, do we have time? We have not. Oh no. All right. So this is what's going to happen now. I've given you 3 sets of things, which are the examples I'm going to go through today, but I probably cannot finish it because there are some very pretty difficult examples near the end. So the tutorial that I've given to you, right, I will go through whatever I can the next lesson. You can take this. I'll go through whatever I can the next lesson, and the rest I'll just send you the solutions. Okay. So circular motion, back to this. A particle is moving, speed v around the radius, The acceleration is given by a equals r omega squared. I will not say more than is needed because you will have the lecture somewhere in May. Okay, somewhere in early May, you should have this lecture. But basically, if your A is r omega squared, just remember this A equals r omega squared for now. Your F is m r omega squared because F equals to ma. Right? So what is r, what is omega? R is the radius of the circle. M is the mass of the object. Omega squared, omega is the angular velocity. Right? What's angular velocity? Right, so velocity is the displacement per unit time. Angular velocity is the angle covered per unit time. That's simply that. Right? And angle is measured in 2 pi, right, in radian mode. So a full circle is 2 pi. Right? That's the conditions here. Okay, so if you have a uniform circular motion, right, your force is always perpendicular to your velocity. You can only change the direction but not the magnitude of the velocity. Listen carefully. If your force is always perpendicular to your velocity, you can never change the magnitude of the velocity, correct or not? To make the v increase or decrease, it must have a component at least in the direction of the force or against it. Agree? Right? So if it's perpendicular to it, it will always be changing only its direction but not the magnitude. Right, so let's try this. Ooh, right, this one you also have. Actually, you all have everything. Huh? So I make it simpler for you. It's suspended with thin wire with length L. The board moves in a horizontal circle with a constant speed V, making the wire a constant angle beta with the vertical direction. Find the tension F in the wire and the period T for one revolution of the board. So if you look at the system, right, it's doing this. You notice that the ball does not go up or down, which means if you resolve the tension, so what are the forces in here is the weight of the ball with the tension sideways. Okay, so there you go. See the red arrow is the tension and the downward is the weight. And these two forces, if you resolve the red arrow vertically, it should be equal to the blue arrow because the object is not moving up and down, it's only moving in a horizontal circle. Simple. Yeah. So, but horizontally, there's no equilibrium, right? The object is moving in a circle, its velocity is changing, which means, right, Newton's first law, what does it state? Right? Object will move in a state of, object will stay in a state of rest or move in a straight line unless an external force acting on it. So this thing is moving in a circle, there must be an external force acting on it. And it's due to the component of the tension acting towards the center of the circle. Okay? So there you go, this is what it looks like. Right? Resolving the tension vertically, it becomes a weight. Resolving it horizontally becomes the centripetal force. Okay, there you go. F in terms of x, F sine beta, which is equal to MA, equals to MB squared over R. Okay, Fy is F cosine beta minus Mg must be equals to 0. Okay, easy stuff. What else I did ask for? Right, so you want to find the tension, right, in terms of, find the tension of F in the wire in terms of what has been given to you, which is the velocity, the length, and the angle beta. Right? Not a big problem. You rearrange this, right, you get this chunk. This is to find the velocity. You have already found the force earlier. Oh wait, the force can just use Pythagoras theorem, not a big problem. Oh. Right, so if you use Pythagoras theorem, you square this side, square this. Sorry, you square this side, you divide the F out. You get sine square beta, sine square, cosine square beta, you add together, it should be 1. Right, then you do the mathematics, you should get this. It's actually not that tough. Right, if you want to find the velocity, you remove the angles by using, remove the unknown's mass by using sine over cosine, you get tangent. So these are the usual strategies. One is to square to remove the sine cosine, one is to put one over the other to find angle beta to velocity. Okay. Your period will essentially be the circumference divided by the velocity. Since your velocity is given by this, you can find the period like that. It's not a big problem. It seems complicated now because I am not giving you a lot of time to work this out. Right? But this is actually what they teach in one whole period of 1 hour. So, yeah, moving on. Negotiating a curve. At what speed can the driver take the curve without sliding? Right. Right. So you have a coefficient friction or static friction S, mu S. Right. What can a driver do without sliding? So there you go. Right. This is the forces. The dot represents the car. There's an upward force on the car and a downward force of the weight of the car, and there's a friction acting inwards, which allows a centripetal acceleration. Right? And the friction is actually given by a component of m, right? F equals to mu m. So vertically it looks like that, horizontally it looks like that. Put that in, you have this, and since F must be smaller than or equals to mu n, you can equate the two equations together like this. So mv squared over r must be smaller than or equals to this, which says that the maximum velocity is given by mu s g r. Okay. Mathematically it makes sense now, but if you feel confused, really don't worry about it. You will master this like nobody's business in a few weeks, no, few months time. Okay. The only difficulty other that you don't learn in your H2 is the mu s part. Mu s part. Any questions? Is that fast? 44 meters per second. Is it fast? It's not fast. It's very fast. Means the 100-meter mark, right? 2 seconds is gone, you know. It's very fast. Can you imagine a car going at that speed? 60 kilometers per hour is about 15 meters per second, is it? Or 25? You can calculate that. Anyway, next. Now you have a curved bank. How many of you watch F1? Okay. How many of you watch cycling competition? Skating competition? No. In the Olympics, Winter Olympics, there's this sport called the luge, where they go down the icy tunnel and they go very fast, right? It's the same idea, right? When they turn a corner, that corner is banked, right? It means it's curved out, and do you see them doing this? When they turn the corner, do you see them doing this? Or do you see them doing this? Which one? The first or second? They bank up, right? Why? Why do they do that? Right? It's because of the physics here. Okay, so let's explore it. It's actually quite nice. Right? Because when you're sliding down the icy tunnel, there's almost no friction, which explains why you need a curved bank. Right? So if you look at this, the normal reaction force, right? There's no friction because you want it to have no friction. To not rely on friction, you actually have the normal reaction force now providing for the centripetal force. Right? And the normal reaction force will have a component, the vertical component is equals to the weight, same, right? But the horizontal component is equals to the centripetal force. So this is somewhat similar to your conical pendulum example. Right? Somewhat similar. Just that your normal reaction force is now replaced by the tension. Once you have this idea, the math is just simple. Okay? We use the same technique. Notice we use the same technique. We take sine over cosine to get beta, inverse tangent this side, you get your answer. It's the same technique. I bluff you now. Okay? Alright, done. Yay. Number 17. Number 17 is a monster of a question. Can you put a star there? Because it's... Oh wait, did it go to 18 straight away? I skipped one. Is it? Oh, this is 17. Sorry, 18 is the one that is a monster of a question. 18 is a really difficult one. A small bead can slide without friction in a circular hoop in the vertical plane. Have you seen this kind of toy before? Yeah, right. I mean, no. Yes. You have like a bead. I mean, you have a few beads on a hoop when you're young, and you like shake it like, hey, when you're a baby. But if you actually spin the hoop, go and borrow your baby brothers and sisters. You can steal from them and then cry. Take it and spin. You'll see the bead actually. If you spin it at a constant rate, you see the bead go up. The faster you spin, the higher it goes up. Right? So the question is, how fast do you spin makes it go up by how much angle? That's the physics about it. Okay, in the Olympiad, we ask you these kind of strange questions, right? So if we let you spin at 4 revs per second, revs mean 4 turns per second. This is the radius. What would the angle beta be? They'd be like, oh, how do I do this, right? Well, we assume certain things. There's no friction in the direction of the circle. There's only normal direction force. So if you look at the force diagram on it, it's essentially the weight and the normal direction force. Right? Once you have this idea, then using what we have learned in example 17 and 16, you can do the same thing. Right? Notice it's exactly the same thing. Although here the radius is changed, right? The radius is actually has a component of sine in it. Sine beta. So what do? Put one over the other, you get this ratio. Right? But then you realize this, right? Previously you get a tangent beta. This one is a completely are all numbers. You can solve for beta, right? But here, oh my. Right? Do you go and do sine square beta over cosine beta equals to v squared over rg and you try to solve this thing? Really difficult, right? Really difficult. Let's see if we can help ourselves out here. Velocity is given by 2 pi r sine beta times f. What's that? Well, 2 pi, this is the radius to this circle, right? Times f. F being the frequency, which is basically just 4 revs per second. So f is equal to 4, right? So this then becomes your velocity. Yeah? So here you still cannot solve. If you sub in this into velocity here, you get this monster. So still doesn't look like it can solve it. No. Because you realize that now the sine goes away, sine and sine squared, this becomes sine. Sine has both left and right has sine, cancel that away, you just have 1 over cosine equals to this monster, then yay, you can solve for B. Yay, easy. No. Right, so it's a monster of question, put a big star. Come back and try this without looking at the answers. Okay. Part B and C is actually a bit more easier. Can it write to the center of the hoop? What do you think? Can it write at the center of the hoop? Yeah, because if beta is 90 degrees, cosine 90 is 0, which means your g is 0, or your radius is infinity, or you're spinning at an infinitely fast rate, which means you have defied the speed of light, right? Cannot be. So cannot be done. Very good, right? Oh wait, there's an angle. If b is 90, this cannot be done. Huh? Cold in here. Part C. Oh, what's part C? Part C asks you what will happen if you're spinning at revolutions of 1 rev per second. It's interesting, huh? You would think that if I'm spinning at 4 revolutions per second, the angle is 81.1. At 1 rev, the angle should be, well, smaller. Don't know whether it's linear or not, but much smaller. Let's see if that's possible. Oh no, if you sub f equals to 1, your cosine is bigger than 1. Cosine beta becomes bigger than 1. How can that be done? Then where's the bit? Has it disappeared? Right? That's why this question is path. Right? You'll be like, Right? It's actually too slow to actually, when you spin at 1 revolution rate, it's actually too slow to bring the beat up. So there actually is a minimum frequency to spin such as to bring the beat up. Huh? So when you go back today and you try to spin your baby brother's or sister's toy and it doesn't come out, it's not because the physics is wrong, it's because maybe you're not spinning fast enough. Right? Or that the physics is wrong here. right? There are new it doesn't apply to the toy that you're spinning, okay? Because friction is actually quite a big component in real life. Any questions about this? Sorry? Can it stay at the top? Can it stay at, by right, you can. If the beat is completely perfectly at the top, and your spinning is so perfectly, it can stay there. Right? Because the tendency of the beat to want to move to the left due to the right, move to one side due to one side of its body is equals to the tendency on the other side. It should stay perfectly there. But in reality, it's an unstable equilibrium. So it will start moving down. The floor, it starts to move to one side. It cannot stay there. You move down further. You move down further. It cannot stay at a certain angle. You go to zero. That's why it should. So top is possible, but it's an unstable equilibrium. Okay. Let me stop.